Rockstars, let's get back to this. We spent the last couple days learning the product rule, the quotient rule, derivatives of trig functions, and those are all some great basic derivatives. However, the chain rule is really the one that controls them all. This is our focus for today. What is the chain rule and how does it apply? We're going to do our normal try to discover the chain rule. It's not going to be so much a proof this time as to intuitively determining what the chain rule tells us. Let's take a look at our brief little opener here. So we're going to assume that a variable is constant if it's not the input. Well, how do we know what variable is the input? I think each of these are written in function notation, so we can probably see the input as we go through here, no problem. So if they ask you to find, of course, y of 3, then we would just replace the x with 3, and it'd be a times 3 plus 3, or if you wanted 3a plus 3, same thing. Okay. If we wanted to do y of 3 over here, now a is the input, so it'd be 3x plus 3. And last but not least, y of ax, this is a function that takes two inputs. So y of 2 comma negative 1 is going to be 2 in for a, negative 1 in for x, plus 3. Negative 2 plus 3, I think, is 1. Now, how does that work with derivatives? Well, derivatives are also going to show you the input here. Because if they ask you to find dy dx, it means take the derivative of the equation or function named y, and when you take the derivative, take it with respect to x. Essentially, treat x as a variable, a as a constant. Well, when we take the derivative of this, imagine if I asked you to take the derivative of 4x plus 3. You'd say, well, the 3 goes to 0, the 4 is a constant, the x goes to 1. It would just be 4. It'd be the value of the coefficient of x. So the derivative in this case, dy with respect to x, is just going to be this coefficient a, right? dy dx, I should probably say, equals a. If we look over here, same idea, but now x is going to be our constant. And so when we take the derivative with respect to a, this is just going to be x. And we're not going to deal with the derivative of two different inputs for today. All right. Now that we've done that, now that we're comfortable with what all those inputs mean, we're going to go ahead and take a look at these derivatives down below. Your goal is to evaluate the derivative at the given x value by hand, and then verify the result using your calculator. So you do need a graphing calculator for this part. If you don't have one, pause the video and get it out. Alternatively, you could do this on Desmos just by typing f of x equals x plus 1 to the 5th, and then if you wanted to find y prime of 2 on Desmos on the next line, you'd type in f prime of 2. But if you have a graphing calculator, and all of you should at this point, you really do need one to be successful on the AP exam, you can't use Desmos, you should be able to do this no problem. So what does this look like? Well, first we're actually going to ignore this u substitution column. We're going to come back to it, and I'm just going to zoom in here for now. So find y prime of 2 by hand. Well, you of course could write out x plus 1 times itself 5 times, but doesn't it make sense that we could probably just use the power rule here? We'd say, okay, y prime, the 5 comes down, x plus 1 to the 4th. I mean, that seems like the power rule. And then they want us to find y prime of 2, so we'd say y prime of 2, that's 5 times 2 plus 1 to the 4th. That's 5 times 3 to the 4th. Ugh, this is going to be kind of gross. 3 times 3 is 9, third 3 is 27, fourth 3, ooh, I think that's going to be 81. So we have to do 81 times 5, but luckily our mental math skills are splendid, and I think we'll probably end up with 405. And then we need to find y prime of 2 using a calculator. I've cheated a little bit here, and I've entered all of these functions into my f of something. As a reminder, when you find the derivative on the Inspire, I'll show you an 84 one later on, but when you find the derivative on here, we want to be on, so we hit this, we don't want to be the graphing screen, we want to be the other screen, menu, calculus, derivative at a point, which is 2. We don't want 1, derivative at a point. And then what variable x, sure, that's fine. What value are we plugging in? I literally don't remember, but it seems to be 2, so that's exciting. And then enter. It says, what do you want to take the derivative of? Well, you could go ahead and type in x plus 1 to the 5th. In fact, most of you probably will do that because you didn't ready this lesson for yourself. So x plus 1 to the fifth is what's going to go in here. However, I prepared ahead of time, and I think that is in my f1 of x. Notice it's bold. It's called f1 of x. So I'm going to go back and just type in f1 of x. It saves me a little bit of time. Enter. 405. I have crushed it. There were cheers everywhere. The crowd went wild. So y prime of 2 using a calculator was also 405. My answers do match. If they don't match, they're off by what they match. So why would they be off? Cool. You have 2 more of these to do. You have 2x plus 3 as well as 3x plus 5. So take a couple minutes, try those. Once you've tried them, unpause this video, and then we will discuss. Okay, you're back to it. Let's run through what you probably did on each of these. You probably said that y prime is equal to 5 times 2x plus 3 to the fourth, which makes sense. And then you'd say, okay, y prime of 2, we're going to get some pretty large numbers here. 2 times 2 is 4, 4 plus 3 is 7. That's 7 to the fourth. I have no idea what that is. I'm going to check that on my calculator. We'll try my trusty 84. It's going to be 5. Let's try turning it on first. It's going to be 5 times 7 to the fourth, and hopefully order of operations is in effect, 12,005. Very exciting. So we got the y prime up, no, this is 12,005. Nice. What about if we found it with a calculator? Well, I have this in f2 of x on my Inspire, so I'm going to do that, right? Realize that we can, of course, copy and paste this down, and then I'm just going to change this 1 to a 2, trying to save some time here. What do I get? Oh, I get 24,010. Well, that doesn't match. 24,010. Right? Definitely not a match between those two. So they do not match. What are they off by a factor of? Well, hopefully staring at these two, you can tell that if you were to take this equation and you were to multiply it by 2, you would get this as your answer. So they're off by a factor of 2. Let's try one more. Okay, do it by hand. We'll do this one in green. Y prime is going to be 5 times 3x plus 5 to the fourth. And that means that y prime of 2 is going to be 5 times, what's that? 6 plus 5 is 11 to the fourth. This is going to be a big number. 5 times 11 to the fourth. Could probably do that by hand, but I don't want to. 5 times 11 to the fourth. And we end up with 73,205. That's the wrong one. Clicking is hard. 73,205. Okay, well, what about y prime of 2 using a calculator? Well, using a calculator, I'll show this one on the 84. I prepared this one as well. Don't forget that on an 84, you can always do math, and then the derivative, the numerical derivative is math 8. And then it says dd what? I'm going to do ddx of what equation? You can type in the equation. However, you'll notice that I already have it in y1 up here. So I'm going to go through and try to get back there, and we're going to go alpha f4. It's in my y1, and I want to evaluate this at x equals 2. I'm getting, whoa, something really weird. I wonder if I made a mistake as I went through and did it. 3x plus 5 to the fifth. I don't think so. This all looks pretty darn good. So then the question becomes, is this calculator being weird, or am I doing something wrong? Or is the 84 just having an issue and maybe I should try it on the Inspire? Let's take a look. So if I change this, you'll notice that I have this set up in f3 of x. So I want to go back to my other screen. I'm going to copy this down. We're going to take this f3 of x right here and come up with 219,615. And notice that this one was 219,615. Oh, it is the same. This is just the 84 doing strange things. It's asking you to take a derivative at a really big value, and at really big values, the slope is going to be more off than normal because, again, the way the calculator calculates the slope is it picks two x values really close to 2, like 2.01 and 1.99. However, if it's a really big y value, then the y values are going to be off by a lot, and so this decimal is going to come into play. So it is 219,615. Okay, you just have to be careful with those 84s. They're not quite as accurate as the inspires. Now, how much are those off by? Well, let's go ahead and just try it. Let's take my answer. I'm going to copy this down and divide it by the previous answer, which was not on this, which is awkward. Our previous answer was 73205. 73205. Hit enter. Oh, it's off by exactly 3. Okay, cool. We probably could have seen that 7 times 3 is 21 and guessed that. They do not match. They're off by a factor of 3. What was the point of this? Well, the point of this was to get you to realize that although the power rule is awesome, it clearly has some sort of a downfall. And that is, if we do the power rule with some functions, we get the right answer, because of course the calculator has the right answer. I mean, the calculator is not going to lie to you. But if we do it with other functions, we don't get the right answer. So what is determining whether we get the right answer or not? Well, hopefully you were starting to put it together and said, wait, we're off by a factor of 2? There's a 2 right here. We're off by a factor of 3. There's a 3 right there. And maybe we could even think, how does 3 relate to 3x plus 5? Well, those of you might say, wait, if we take the derivative of 3x plus 5, that's 3. The derivative of 2x plus 3 is 2, and the derivative of x plus 1 is 1. So maybe they're off by a factor of 1 because they're not off at all. And it turns out that, yeah, that is what the chain rule is telling us. Now, we have 2 different versions of the chain rule, and they're both good. I tend to use version 2 more than version 1. Your textbook calls them version 1 and version 2. However, it is important to know both of them because sometimes on especially multiple choice questions, they'll phrase the chain rule in terms of version 1, or the other times they might phrase it in terms of version 2. So we need to be comfortable with both of them, and so let's look at what they're telling us. This says, if you take the derivative of some function y, then the derivative is going to be the derivative of y with respect to u times the derivative of u with respect to x. Now, what does that actually mean? Well, where is u coming from? We're taking the derivative of y with respect to x. Why is u even important? Well, the idea behind this is we're going to make a u substitution to make the inside function in a composition. What do we mean by that? Well, we'll see it in a second. A simpler function u. However, we do need to remember to take the derivative of u at the very end. So basically, we're going to make a u substitution and take the derivative of that function. And then we're going to multiply the overall answer by the derivative of our u substitution. Let's try to use that right now. Let's see what it looks like. So I gave an example on this first one on the previous page. And I said, well, this little x plus 1 here is kind of strange. So we're going to make that more simple for now. We're going to let u equal x plus 1. And what we're going to do is now we have an equation that is the power rule, right? This is what the power rule says. If you have a function to a power where it's just x to a power, u to a power, q to a power, we know how to do that derivative. Well, the derivative of this function with respect to u, because u is the input variable, is 5u to the 4th. Technically times 1 if you wanted, but we'll get more onto that later. Where does the times 1 come from? Well, let's think about my u substitution. If I take the derivative of my equation u with respect to x, then the derivative of x plus 1 is 1. This comes over here. So what this is telling us is if we take the derivative of y of a u substituted function, and I should use different colors here, then we take the derivative of the u substitution like normal. But because we did a u substitution, we need to account for that. And whatever the u substitution was, we have to multiply by the derivative of that u substitution. Then, once we've come up with that, we can put everything back together. And we can say, well, we took the derivative of 5u to the 4th, but we know that u is actually x plus 1. And then there still is the times 1 at the end. Now, this seems kind of silly because we're multiplying by 1, but let's see it in effect with the next one. We need to make this look like the power rule. It needs to be y equals just something simple to the 5th power. In order to make that something simple, we're going to let u equal to the interior of the function. Notice this is a function composition. Someone plugged 2x plus 3 into the function x to the fifth. Alright, that looks pretty good. Well, now let's go ahead and take the derivative. So to take the derivative with respect to u, right, and I'll show this in two different stages. dy du, the derivative of y with respect to u is just 5u to the fourth. However, the derivative of u with respect to x, du dx, is going to be, well, the derivative of this is just 2. But what's the overall answer we're looking for? Well, this equation has y and x. So the overall answer that we're looking for is dy dx. And dy dx is found by doing dy du times du dx. The derivative of the main function times the derivative of the u substitution. And as we go through, dy du was, of course, 5u to the fourth, and du dx was 2. If we clean this up a bit, and we probably should, instead of 5u to the fourth, we know that our u substitution was 2x plus 3. And then we might want to combine the 2 and the 5 to make 10 times 2x plus 3 to the fourth. Okay. Let's do one more. Let's try to do it a little quicker, though. U substitution. Well, my u is going to be 3x plus 5. That gives me that y is equal to u to the fifth, which means that y prime, and now you might start to see the downfall of the Newtonian notation, because y prime, we're like, wait, is that dy du, or is that dy dx over here? So instead of y prime, let's just go straight to our answer. Let's say dy dx. dy dx is going to be the derivative of the u substitution, which is dy du, times the derivative of the u substitution, which is du dx, and that is 3. Putting this all together, then, we get 15 times, and my u substitution was 3x plus 5 to the fourth. Chain rule. Now, before we even explain why it's called the chain rule, we need to go through version 2, because, full disclosure, I like version 2 more than version 1, and in fact, I will very rarely refer to version 1 for the rest of this. It will come up and we will practice it, and on your homework there are going to be problems that have asked you to practice it one way versus another, and you should, because again, the multiple choice will ask different ways to phrase this. But ultimately at my core, I always think of this version 2 as my main version. So, what is version 2? Version 2 says that if you have some function of x that's made up of a function composition f of g of x, then the chain rule states that to take the derivative, we do the derivative of the exterior, the outside function, and we leave the interior function the same. But then we have to, because we didn't account for the derivative of the interior function, we have to multiply by the derivative of the interior function. So what does that look like? Well, I have version 1 and version 2 here. I'm actually going to start with version 2 and then we can go back to version 1. What we really need to be good at to use version 2 is to understand which is the outside function and which is the inside function. For example, 2x to the fourth, doing this little sidebar over here, we need to realize that we had x to the fourth, and then we took 2x and substituted it in for x, which means my exterior function is the fourth power, and the interior function is 2x. So what does the chain rule say to do? The chain rule says do the derivative of the outside function first. Well, how do we do the derivative of something to the fourth power? We bring the fourth power down, we keep the inside the same, and we get a third power. That is this first part right here. Do the derivative of the outside, keep the inside the same. We did keep the 2x the same. But then what? Well, the second part of the chain rule says now that you kept the inside the same, we do have to account for the derivative of that. So I'm going to do the derivative of 2x, which I think gets us 4 times 2x cubed times 2, or 8 times 2x cubed. Now you might ask, wait, can I go straight from here to here? Certainly, there's nothing wrong with that. However, I just wanted to show all the steps to get there. Okay, well, what does it look like using version 1? That's our u substitution coming up, right? We know that u is 2x and du dx is 2. So the derivative of all of this is going to be 4u cubed times du dx times the u substitution, which is 4, what was my u substitution? 2x times du dx, which is 2, or 8 times 2x cubed. Hopefully that's the same. Yeah, we've done really well here. There are a couple more of these that you should try. Once you are done with them, I'm going to quickly do them. Probably all doing version 2 because we haven't done that one as much. I'm going to quickly do them so you can check your answers. Take about a minute or so, and then once you've tried them, unpause. Please do them in both methods though. Okay, hopefully you're back with us. Let's look at this version 2 stuff. Version 2 to me is just a little bit more straightforward than that extra u substitution, but the u substitution makes it a nice way to break it down. So what are we doing here? Well, my exterior function is again that fourth power, so we do the derivative of that first. Chain rule says keep the inside the same, and now multiply by the derivative of the inside, 2x plus 3. However, if you left your answer like this, you would absolutely lose the point for the answer because that's not the right answer. Why is it not the right answer? Because PEMDAS tells us that you're doing all of this first, and then you're adding 3 at the very end. This multiplication takes precedence over the addition. So we need to be very careful, especially when using the chain rule, to group the derivative together so we see the derivative is multiplying by the entirety of that first part, that dy du, if you will. Can you clean this up further? Not too much. You could rewrite this as like 4 times 2x plus 3 times x squared plus 3x cubed if you wanted, if that makes you feel better, but there's nothing too much else there. Let's get to this last one, because hopefully you realize this last one's a weird one. You're like, wait, we've been doing the derivative of x to the fourth for like 2 weeks now. Are we about to learn that we were wrong? Well, no, you weren't wrong. You just weren't seeing the derivative for what it really was in its complete form. So let's apply the chain rule here. d dx of x to the fourth. Well, the fourth power is again the exterior function, the outside function, so we do the derivative of that, and we keep the inside the same. And then what do we do from here? Well, we need to multiply by the derivative of the inside, which is 1. Now you can certainly simplify that to 4x cubed, but realize that the chain rule is always there. In fact, every derivative we have done so far has used the chain rule for the last 2 weeks. I've just purposely picked them so that the chain rule hasn't negatively or incorrectly affected your answer. By knowing the chain rule, we've now unlocked a huge field of derivatives that we didn't even know wasn't there. Right? You only took the derivative of sine of x, but what if now we have to take the derivative of sine of 2x? We can do it with the chain rule. Right? We're going to get a more complete understanding of what e to the x is. Of course, we still don't actually know why it's called the chain rule. That's kind of strange. Well, the chain rule, at least the way it was described to me, is you kind of have to think about like a link of chain, like those chains. You have like your little piece like this, and then there's like another piece that connects over here, and then another piece that connects over here. You have to think about this chain link, and imagine it's like rolled up. And I may have in the past used the example of like whipping somebody with this, but maybe that's not acceptable for a teacher to say. So instead of saying that, we're just going to think of like unfurling the chain. You let the chain, let's say that it's all curled up in your hand, you let the chain links unravel. Well, what's going to happen is the first chain link is going to fall out, and then it's going to have the next chain link follow it, and then the next link, and then the next. It's like you have this big master link, but then a link comes out after that, and that link comes out after, and after. And so what we're going to find out is that the chain rule that we've done so far has only had 2 links. But what if there is another chain rule inside and we have another link and another chain rule and there's another link? And we could really go infinitely far if we wanted. But that actually brings me to one of the weirder comics I've ever found about calculus, but it always entertains me, so I include it. And we can, of course, cite our source down here. It came out in 2006. So to the right's a really weird comic, but it does kind of illustrate the idea of the chain rule, right? Differentiate the mother, so this is the mother up here, right? D mother dx. Well, how do you differentiate the mother? Well, you leave the baby inside, and then you differentiate the baby, which is really kind of creepy. But we need to realize that the mother represents the outside function, and the baby represents the inside function. And you work with the mother first, and then you work with the baby, right? You work with the outside function and then the inside function. So again, very strange comic, but it makes me laugh in kind of a weird way each time. So I always like to include that. Okay, now this is normally supposed to be done in groups, but we don't have groups, so it is what it is. We are going to go through 6 questions. If you are working with someone else, then you'll only have to do half of the problems because one person is going to tell you what to write and you're going to write down what they say. So they're doing all the thinking, you're doing all the writing, you can't help them. I usually call it a dictator and a scribe. The dictator is telling you what to do, the scribe is actually writing it down. However, what I'm going to do is I'm going to skip to a problem and then have you work out the answer. And then once you've worked out the answer, we're going to see how you did. So let's go ahead and jump to our first problem. Okay, your goal is this. Given f of x equals 5x plus 4 cubed, find f prime of x. I'm going to quickly pause here so that you can work through it. And then once you're ready, you can hit unpause and see what the right answer is. Okay, well, your right answer here, and I can write right on this, which is very nice, I think should be something like 3 times 5x plus 4 squared times 5, right? The derivative of the inside. And you could, of course, have cleaned that up to 15 times 5x plus 4 squared. Nice. Okay, doing well so far. Hopefully you're ready for the next one. So let's try the next one. Ready, set, go. This one's a little trickier, isn't it? I think it might have helped you, and maybe you need this hint, and you can go back and try it again to rewrite this as the sine of x, all of that cubed, right? That's what that cube on the inside between sine and x means. So try it again. Okay, so either you're still stuck now or you're ready to check your answer. Answer-wise, it's a little tricky. The exterior function is the cube, right? So it becomes 3 sine of x, keep the inside the same, sorry about that extra line, squared. Chain rule. The derivative of sine, hopefully remember, is cosine. If you wanted to write this a little bit nicer, I don't know why we went the other direction. We can slide back over here. If you wanted to write this a little bit more nicely, you could say it's 3 sine squared of x times cosine of x, but you don't have to do that. All right, let's try another. Ready, set, go. Wait, is this the same problem? No, it's actually not the same problem. Now, what they're trying to trip you up with is where that cubed goes. If the cubed is at the end, it's assumed then it's sine of all of that cubed. So maybe that helps you think about it, and then when you're ready, unpause me. Yeah, so hopefully you notice that the exterior function this time is sine, right? This is the function sine of x with x cubed composed inside of it. So x cubed is the inside, sine is the outside, which means then that when we do this derivative, we need to do the derivative of the outside first, which is cosine. That's the derivative of sine, and keep the inside the same. And then we multiply by the derivative of the interior, which is 3x squared. So, looks similar, definitely not the same. Let's go again. Ready, set, go. Wait, is this like a crazy function inside of a function? Well, yes it is. So f of x here is probably best thought of as sine of x cubed, and then all of that cubed. How does it work? Well, f prime of x, we bring the 3 down, that's my outside function, sine of x cubed stays the same. And of course, this is a square. Okay, let's work the interior. Well, how do we do the derivative of sine of x cubed? We just did the derivative of sine of x cubed. It was literally the previous slide. We do the outside function first, cosine. But wait, we still haven't accounted for this inside piece yet, and so we need to multiply by the derivative of the inside. Notice this is a chain rule inside of a chain rule. We have those 3 links of chain now, right? Something like this, okay, where you have your first link, your second link, and your third link all unfurling. Okay, let's try another. Ready, set, go. A hint, you say? A hint? Okay. Well, hint-wise, maybe think of this as 5x squared plus 1 to the 1/2 power. Remember, we're not allowed to distribute a square root. That's definitely a no-no. Try again. All right. Well, f prime of x, exterior function, 1/2 power. It's the square root for sure. 1/2 times 5x squared plus 1 to the negative 1/2. Are we done? Well, I don't think so, because we need to account for the derivative of the inside, and that's going to be 10x plus 0 if you wanted to group it like that. I would probably just write this as 10x though. Can we clean this up? Should we? Well, yes and yes. We can of course do half of 10, and half of 10 is just going to give us 5x's. I think the 5x has a positive exponent, so it's going to stay on the top of the fraction. 5x squared plus 1 has a negative exponent, so it's going to drop to the bottom and look something like this. Okay, almost done with this. Let's try one more. Last one. Well, they're asking us to calculate h prime of 1 and h prime of 2, and I think in order to calculate or evaluate something into a function, we need to know the equation for that function first. So before I evaluate anything, let's go ahead and find h prime of x. So h prime of x, how do we take the derivative of this? Well, it has an outside function and a function that's composed inside. So the derivative of the outside function, f prime, keep the inside the same, and then of course multiply by the derivative of the inside. I bet we can do the math now, right? You work with the bottom of the screen here. We need to go ahead and find h prime of 1. That's going to be taking me backwards, which is awkward. We're going to go ahead and work with, and this can be touchy because it's the bottom of the screen, we're going to have f prime of g of 1 times g prime of 1. Well, let's clean up one of these first. I think g of 1 is 2, so f prime of 2 times, I don't know why I had that extra parenthesis, times g prime of 1. Cleaning this up further, f prime of 2 is 7, and g prime, I do want to keep all my annotations. Thank you for asking. I decided to end my PowerPoint. That was so exciting. And now it wants to do nothing at all. Very, very cool. I love all those annotations. Let's come back here and let's start my slideshow from the current slide, please. There we go. And we get 7, and g prime of 1, that's over here, is 3. And I think I'm looking at 21. Well, that was h prime of 1. I bet you can probably tackle h prime of 2 now that we've done h prime of 1. H prime of 2 is f prime of g of 2 times g prime of 2. Let's see, g of 2 up here. Let's get rid of this little line, which apparently is not going to happen, so that's fine. G of 2, let's see, g of 2 is 1 times g prime of 1. F prime of 1 is 5, and g prime of 1 is 3, which gives us 15. Right? Always important to focus on these from multiple different methods. That was from a tabular, or sometimes you'll hear it called a numerical method. There's actually a course called numerical methods that is dreaded by many college students, numerical approximations. But we got through that just fine, so let's see what we have left to do. Oh, we get some extra practice problems. I love this. You, of course, should try this entire page, see what you can do, and then once you're done with the page, unpause and see how you did. And we're back in action. We're going to need h prime of 1 and k prime of 3, so I think that probably means, and let's write this maybe somewhere up at the top, we're going to need h prime of x, which is definitely f prime, derivative of the outside, of g of x times g prime of x. And we're also going to need k prime of x for b, derivative of the outside function g prime, keep the inside the same, g of x, times the derivative of the inside function g prime of x. Look at all the g's there. Okay, let's rock and roll. H prime of 1. Well, h prime of 1 to me seems to be made up of f prime of g of 1 times g prime of 1. This is like what we just did on the PowerPoint. We got this. G of 1, let's see, it's set up slightly differently. G of 1 is 4. And I always like to just do the interior function. I realize you could do g prime of 1 earlier. I just think it looks nice this way. Totally up to you. Okay, so then we have f prime of 4, which will be 7, and g prime of 1, which will be 9. 7 times 9, which is 63. Okay, what about b? K prime of 3. Well, this is going to be k prime of 3 equal to g prime of g of 3 times g prime of 3. Should have left myself more space, but that's okay. We live, we learn. G of 3 is 5. And then, let's see, g prime of 5 is negative 5. And g prime of 3 is 3. So that to me looks like negative 15. Cool. So that all went with problem 1. Problem 2 is a little bit different. Problem 2 is going to ask for the derivative of a function f of x. And we don't know what f of x is, so I think we're going to have f of x in our answer. But let's take a look. We have y equal to the cube root of f of x. And the cube root of f of x we don't know much about, but if we rewrite this as f of x to the 1/3 power, we might be in a better place. Derivative of this, well, y prime is going to be, we bring the 1/3 down, f of x stays the same, to the negative 2/3, right, 1/3 minus a whole, and we're not done here. That chain rule, we need to take f of x and multiply by the derivative of f of x, f prime. We can actually clean this up quite a bit further, and I'm going to show it in a couple steps. We're going to get 1/3 times 1 over f of x to the positive 2/3 times f prime of x over 1. And I think this will finish up with f prime of x divided by 3 times the cube root of f of x, and I'll put the square on the outside, mostly because I ran out of room. And there we go. Last but not least, assume f is a differentiable function. What does differentiable even mean? We haven't even talked about that word. Well, that's crazy. Differentiable means able to be differentiated. And you're like, oh, okay, did you just use the words in their own definition? Yes, I did. Able to be differentiated. Well, if you differentiate something, differentiating means take the derivative. So able to be differentiated means you are able to take the derivative. Now, what do functions look like that aren't differentiable? We're actually going to cover that in a later class, actually very, very soon to now. But for now, just assume differentiable means you're allowed to take the derivative. And you're like, aren't I always allowed to take the derivative? Not always. So we'll come back to that later on. F is a differentiable function whose graph passes through this point. Suppose g of x equals this, and the line tangent to the graph of f is this. Oh, I always like to break this part down first. We'll do it at the bottom. This is tangent to the graph of f. If I wanted to write the tangent line to f, yeah, it'd be f prime, right, of what? Well, where is this tangent? It's tangent to the point at 1, 4. So f prime of 1 times x minus 1 plus f of 1. And we can go even further here. We know that this tangent line, f prime of 1 is the slope. We know that's 3. So keep in mind that f prime of 1 is going to be 3, x minus 1, and then we know f of 1 is 4. And so I always like to rewrite the tangent line like this, so that in that case, if you're ever asked what f prime of 1 is, you know. And if you're ever asked what f of 1 is, you also know. So this tangent line is tangent to f, and that might become important. All right, evaluate g of 1. Oh, this is crazy. Mr. Grant must have made this up because there's no calculus here. G of 1 doesn't require a derivative. It just requires my g of x equation. F of 1 squared is f of 1. What is f of 1? Ha-ho! Coming in handy. F of 1 is 4. Crushing it. All right, part B, g prime of x. Well, that's going to be, of course, the derivative of g of x. So g prime of x is going to be equal to the derivative of the exterior function, f prime, keep the interior the same, times the derivative of the interior. Doing well so far. G prime of 1. G prime of 1 is going to be f prime of 1 squared times 2 by 1, or f prime of 1 times 2. F prime of 1, we know that one as well. Look how well prepared we are. F prime of 1 is 3, and 3 times 2 gets us 6. An equation of the line tangent to the graph of g when x equals 1. Well, don't we already know that? Didn't we get that right here? Oh, okay. Didn't trick you at all. It's the graph of g. This is down here is the graph of f. So let's do the same thing. Let's create our tangent line. Yeah, our tangent line is going to be g prime of 1 times x minus 1 plus g of 1. And this problem is so clever because it set you up g of 1 and g prime of 1. So I think we can skip right to our tangent line very quickly. I'm going to leave two little gaps right here. We found that g of 1 was positive 4, and we found that g prime of 1 was 6. Nothing too crazy here. However, your assignment for tonight might be a little bit more crazy. The chain rule tends to be pretty brutal, especially if it's buried in, say, the quotient rule. Can you imagine the quotient rule with the chain rule? So you're taking the derivative of the quotient rule, and then you need to remember the chain rule, and oh yeah, it exists. So definitely spend some time on the assignment tonight and really look at my solutions. I tried to show every step pretty carefully, and if you're still stuck, reach out to me so that we can go through it before class tomorrow. I would say the chain rule can get pretty complex pretty quickly. Now, are all the problems in AP Calculus that complex? No, certainly not, and we'll get bunches of practice. But keep in mind that there is oftentimes more to the chain rule than meets the eye. Alright, I think that brings us to the end of today. Thank you for hanging out and learning some more calculus and seeing some weird comics and getting some good practice problems in. I wish you the best, and I'm excited to see you back for day 21.